to this joint colloquium of ESS and MAX4. And we have invited today Regine Willumeit, who I personally have known for quite some time. You'll see that from when I explain her vita. So she has started her career with neutrons, you know, that's really good. Very early on, she did her diploma thesis on neutron activation analysis, if I remember correctly, at the Geesthacht reactor, which, you know, Geesthacht operated a reactor source for a long time. That's where the competence in neutrons comes from. And then she actually built and operated and did a PhD on a SANS machine, small angle neutron scattering machine, which had an in situ NMR device to do contrast variations on very complex biomolecules, on ribosomes and things like that. And she did a PhD on that. And then she operated that instrument as an instrument scientist. She became the head of the department responsible for that instrument. And during that time, this was when I joined HZG, actually, which actually had a different name, and I just learned that they'll change their name again. And then we worked together as department heads. Then later she became department head in my institute. And then actually she made a very good career. She started her own institute at the Helmholtz-Zentrum Geesthacht. And for those who know the German research system in the Helmholtz Society, there's a program-oriented funding, and she now has a very important coordinating role in that because she's representing essentially all the material research done at Helmholtz-Zentrum Geesthacht, which goes far beyond what she is doing in the relevant program and the topic in the Helmholtz Society. So she has a very visible role nowadays, well beyond the Helmholtz-Zentrum Geesthacht. She also was, so she is a well-known neutron scientist, but as you can see from her research, she has moved far beyond that. She's doing many other very interesting things now, including synchrotron and very nice material research. She has been actually part of the scientific advisory committee of ESS, and she has been active in very many other advisory committees at ILL and many other places. So I'm really happy to have her here today. Of course, I would have preferred to have her personally here in a real meeting, but we all know that that's not possible. So this is the only way we can actually continue to do our joint colloquia. And she will talk today about biodegradable magnesium implants, ready to use or fake news. And we all hope it's not fake news. So the floor is yours.
Yeah, thank you very much, Andreas, for this really nice and kind introduction. I feel really flattered by that. And I hope I can meet your expectations now. So I will share my screen now, and I hope that you can see it all. So please give me a feedback if the presentation is visible now.
Yeah, looks good to me.
Good.
Looks good to me. Somebody in the attendees is having some problems seeing, so I'm trying to get some feedback from a few others as well. Just give it a minute, please.
Okay, then I will just wait a few minutes or a minute. So yes, indeed, as you can see from my title, Biodegradable Magnesium Implants, I left a little bit the field of neutron scatterings and moved into the materials research field, but still large-scale instrumentation at the moment, mainly for synchrotrons, but we also hope to go back to neutrons, is quite important for the research, and that's what I wanted to show you, or will I show in my presentation here.
The overwhelming majority seems to see your slides okay, and you as well, so please go ahead.
Good, okay. So we are investigating this biodegradable magnesium implants, which I don't know, maybe some of you have heard it, but normally the people are not aware that it is possible to make a metal implant which degrades. However, this is an idea which has been studied quite a while. So magnesium, a few years after it was discovered, the people thought, let's try and use it as a medical implant. And you see here some examples what the people tried. So some connectors for nerves or the intestine, like here, where you have a magnesium piece. And at that time, the people were not really knowing and expecting that the stuff would degrade, but it was just another material, another metal, which you could use as a biomaterial. So there were different attempts also for bone applications, as you can see here. And this is a clip to close a vessel where the people thought, this is a material as any other metal, let's put it in the body and treat patients. The problem was that almost as long the people realized magnesium is not a metal as any others. And what you see here, it's a fracture of the upper arm. Here you can see the fracture line. And the people have operated this boy and made a plate and some screws here and there. And here you see the sketch by magnesium to fix this fracture. And then after a while, the boy and also the doctor saw there is something changing, and they did another X-ray after 3 weeks. And you can see there is a huge gas bubble, obviously, or at least an area where there is not much tissue. Part of the plate was gone, and unfortunately, part of the bone was gone as well. And you cannot see if the fracture was healed or not, but you could just see this huge damage which was taking place while the material was degrading. And that is because this material, when it is in the right condition, I would say, it interacts with the surrounding liquid. And we have in principle a very simple reaction what takes place, which leads to severe changes in pH, which leads to hydrogen formation, and which leads to a lot of magnesium ions which are released. So we have, when the material is uncontrolled, degraded, a lot of changes which is not good for our tissue. And that was the reason why, even though it was tried at the beginning of last century, the people then refrained and said, well, it's too tricky, we don't need this, we don't want this. So we have other materials which are much more handy, so forget about magnesium. Still, the idea to have a load-bearing metal which disappears over time, where you don't need a second surgery, kept in the mind of people. And I can tell you already, without interfering with my presentation, we have this material in the clinic now. And here are the two examples which are coming from Germany. We have a stent, the Magmaris stent from the company Biotronic, which is on the market now, I would say, for 2 or 3 years. And 5 to 6 years, we have the Syntelix compression screw, and they have now, I think, 6 or 7 different designs of a magnesium screw. Their first one was here for a foot application, and now they have little screws, pins, plates, and so different geometries for other locations in the body. So it works in principle. Why? Because we have understood a lot about the material itself. And I come to this a little later. However, we are not at the end, because otherwise we would of course stop our own research. And here is an example of this Syntelix screw, where there was 1 out of 39 patients which reported some swelling, reddening, pain. Yeah, and you can see here there is the place where the operation should take care. Here you see the magnesium screw after 6 weeks, and you can see it here as well. And only in the CT you can see there is some area, we don't know what it is actually. So the people usually say, sure, it's gas. Actually, there is some tissue. It's non-mineralized tissue, but that's another story. And so we can see that in some cases, this material is not interacting in the way with the body as we want it, and it's not degrading the way we want it. So we still haven't fully got to the point that we know exactly what we do here. It works in many, many cases, but there are, like with all new implant materials, cases where we observe something which is not as expected. And that's where our research kicks in. So what we do is, on one hand, we want, in principle, we want to tailor the degradation. Of course, we want to optimize the whole thing for different properties, that it's biocompatible, that we have the right strength for the specific applications, that the ductility is right, that we can transform our material. But as a starting point, the corrosion resistance is normally what we are tailoring. And we have several, basically 3 ways to tailor the corrosion resistance. We can use alloying elements, we can use different processes, and we can use coatings. We focus in my institute mainly on alloys and processes. Coatings would come into a later stage. And for the alloying development, we have a lot of different alloying elements available. It's a real big toolbox, many of them coming from industrial applications, automotive applications. So aluminum, for example, is a fantastic alloying element for different properties here, which are all really nice to tailor. But aluminum, you will never get a medical approval if you use that, because it's considered to cause neurodegenerative diseases. So whatever we have here as possible candidates, we first have to prove that they are not, even over a long period of time, accumulating in the body and causing some diseases. So part of our research is the study of the interaction of alloying elements in cell culture. Now, beside all this, you can also use alloying elements to functionalize your material. For example, we can use silver, which gives us here some good properties, but it has also an antimicrobial function when the material degrades. So that's where we are picking specific alloying elements, not only for the purpose to tailor the degradation or the strength of the material, but also to functionalize it as a cancer treatment or for antimicrobial treatment, or to support tissue regrowth, because some of the ions, and especially magnesium, is quite useful for that. So what we need for the alloy and process development, or for the alloy development in the first place, we want a very homogeneous microstructure, and we want that whatever we use as alloying element is completely dissolving in our matrix. On the other hand, this is normally not good when you want good mechanical properties. So we have to find somehow a compromise between the corrosive and the mechanical properties. And for this, it would be really nice to predict which phases are formed when we mix different material, different atoms, and what does the microstructure in total look like. So a prediction would be nice, and there are programs which can predict phase diagrams. However, even for a ternary alloy, so with magnesium plus 2 alloying elements, this becomes quite complicated. And some of the really good alloys, they have 4 or 5 components, and it's absolutely impossible at the moment to calculate this. And what we are using here is synchrotron methods, diffraction and tomography, to in situ see which phases and which microstructures develop. And this is then fed back into the thermodynamic calculations of phase formation in alloying systems. So what we do, for example, we have here a dilatometer. These are some examples from DESI, where we have our samples here. And while we are heating up our magnesium to bring it, to melt it completely, and then we solidify it. And through this change in temperature, we observe which phases are there. And then in the end, you can analyze the peaks which you get. It's quite trivial. And we can see that for such a ternary alloy composition, we see these phases, these 3 phases. And you can also see that except for this one, the other 2 which we see were not predicted, and the one which was predicted didn't show up. So with this in situ measurements, we have a very nice tool to support the thermodynamic calculations in terms of phase formation. Of course, we do not only want which phases will we get, but what is the structure of the phases. And for this, we have a colleague, in this case, it's Domonko Stolnai, who is doing very fast tomography. Again, this is an example from DESI, but he's also working at the ESRF with a 20 milliseconds exposure time, where he can have a full tomogram of within 25 seconds. And then we can visualize how the solidification process in this piece of magnesium is taking place, which microstructures are formed, and how. And that is very important, again, for the understanding of this material. Of course, we are also looking into how do processes like extrusion, for example, or we have also powder metallurgical processes, how they are influencing the microstructure. And there is really a lot to do. Unfortunately, we do not have in situ experiments here, but we would love to look how processes are changing our material. Instead, we look very much into how are our materials corroding. And for those who are not really familiar with that, we have here our magnesium matrix, and this is the standard process which we always observe. However, we are normally not doing our experiments in water, but in something which is closer to our body fluids. So we have precipitates of hydroxyapatite, for example, forming. We have CO2 in our environment. I come to that point a little later, which dissolves here. And then we have carbonates also precipitating. We have chloride ions, which also support strongly the corrosion. So we have many processes, and we would like to understand which process does what, how are they interfering, and how is then the corrosion process with respect to the certain microstructure we have here taking place. Now, this corrosion understanding is essential to understand how our material interacts with the body. And here I brought a very simple sketch how people think a non-degradable metal is interacting with the body. So we have, let's assume this gray here is a piece of titanium. We have a more or less neutral pH in the body. And then we have interaction of small ions, electrostatic interactions. And this little gray line here, that's the oxide layer. And here we have the interface where the interaction takes place. A little later, we have larger ions, then the organic compounds can take place to settle down here. Of course, they are also interaction with the ions and so on. So we have a kind of protective layer formed, and then the cells come and form the tissue, very simple. So in the case of magnesium, I told you already that the degradation is a complex thing. And by the way, we also have to include diffusion of flow for some cases. And when we switch to magnesium, we have again the same interaction, of course, but at the same time, while these ions are getting close to the surface, we have the degradation process. And remember, we have pH changes from neutral to basic. Normally, we have ion release and we have hydrogen release at the same time. So, and then obviously everything else is changing. And we are not ending up with a thin oxide layer, but with a massive degradation layer. And for us, it's very important to understand how is this formed? How is this interacting with the solution around? How is it interacting with the cells? And what is, for example, the mechanical stability of this interface when we think in terms of a real implant? So just some steps back for the corrosion of magnesium. I just mentioned when magnesium normally corrodes, the pH becomes very basic. Normally the corrosion of magnesium in water stops as a pH of 10, which of course is completely unacceptable for tissue applications. And my colleague Svetlana Lamarka did a very nice scanning ion selective electrode scan over a piece of magnesium. This here is where she scanned along the sample. In a very simple salt solution, 1 hour corrosion, 2 hour corrosion. And we can see in the upper row, yes, the pH is here 10, even beyond. And over time, 1 hour, 2 hour, the corrosion, the pH change diminishes a little bit, which means we get a protective layer, but it stays on a very high level. The same experiment with a little bit of calcium, you see the pH stays more or less around 8, which is very nicely tolerable for cells. So already the first thing which we learned about magnesium, that the pH always gets very high. In a living system, does not. Locally, close to the surface, the pH stays on a level that the cells can survive, and that is because in the presence of calcium, we form a protective layer. This is true for different alloying systems, and only when the degradation is not extremely fast. But with a moderate degradation, we observe without calcium the standard electrochemical degradation behavior with some calcium, very slow, very nice. So protective layer is formed. That brought us to the point to say, well, let's use this. Why not putting calcium in the alloy? And when this releases, we automatically have a protective layer. Unfortunately, I can show you here, it doesn't work. Yeah, we see more or less the same behavior without calcium and with calcium, even when we have calcium in the material. And the reason for that we have only so little calcium coming directly from our material that it is a non-measurable effect here. If we would increase the amount of calcium, we would probably see the same effect directly on the surface formation of a protective layer. But when you increase the level of calcium, the corrosion is also accelerating. And then it corrodes so fast that there is basically no time for a protective layer to form. So that was a nice idea, but unfortunately, we cannot make use of the special alloying process here in this case. But anyway, we now know the pH is relatively low and still tolerable for cells. Now, the degradation rate can be influenced by many things. For example, if I have a piece of magnesium and I put it, this is a cell culture medium, at room temperature and air, I have a certain corrosion rate. If I increase to body temperature, corrosion rate goes up. If we increase the CO2 level, as it is available in our blood, for example, we can see from the standard technical condition to our body environment, the degradation rate can easily double. So we have a severe effect of the presence of temperature and CO2. Plus, when we add some proteins to the whole solution, the degradation goes down again. So in principle, we were with the problem that we have in a biological living system, possibly tens or hundreds of different factors which can influence now the way the material is degrading. And we came across the CO2 as being a quite important factor because the amount of CO2, the availability of CO2 during the corrosion process defines which corrosion products are formed. And this in turn defines how the solubility is depending on the pH. So we have an extremely dynamic system. And what we do at the moment is that for certain time points, we analyze what are the corrosion products. What we want to see is, of course, the time course. We want to see the development. And I will show you later how nicely synchrotron radiation does help us here. I mentioned we have many factors and we have proteins, of course, involved in the whole story. And you can see here the degradation rate, which we determined in a salt solution and in cell culture medium. And in salt, it's rather high. In the cell culture, it's already very low. Why is that? Because we have calcium in the cell culture. And we have these carbonates in the cell culture. Those helps to form a protective layer. But we see also, even if those factors are not there, if we add proteins, bovine serum albumin or fibrinogen, that can also drop significantly the degradation rate, especially here in the salt solution. So proteins can play the same role as calcium. So of course, everybody said, clear, it's a protective layer. But it's not like that. It's not so simple. So the first thing we did was that we measured the protein adhesion during the degradation. So we put BSA and fibrinogen in the electrolyte while we were degrading, and we could see afterwards by fluorescence microscopy that the protein was actually found in the degradation layer. So it's not a protective layer on top of the material, but this layer becomes protective because the proteins are inside that layer. We were then wondering, okay, if the proteins are built in the layer, what happens if the layer is already there? And then we could clearly see that in the case of the simple salt solution, the proteins can adhere. This is the BSA, here is fibrinogen. In both cases, in the salt solution, they adhere. In the cell culture medium, the proteins didn't like to adhere. And we were wondering, how can that be? The answer is because we have, in the case of the cell culture medium, the calcium kicking in, and we have the formation of calcium carbonates, which is not the case here. That was the hypothesis, and we tested it. We prepared the different magnesium and calcium carbonates and phosphates. We put the proteins to it, and we measured the absorption. And we can see for this part, they absorb, in here, they don't. And when we quantify, we can clearly see that the fibrinogen and the BSA don't like to attach to the calcium containing phases. And we thought, okay, so obviously whenever we have calcium in the medium and a protective layer with calcium is formed, protein adhesion is hindered. And indeed, we did here a lot of measurements with different solutions in salt, with all sorts of combinations, with glucose, with different other salts, with amino acids up and down. And only where calcium was present, we see that there is no protein adhesion possible. And that brought us to the point to ask, okay, why? And we think it has something to do with the electrostatic interaction, because the BSA and the fibrinogen for rather high pH is negative. And we do have an attraction with the magnesium carbonates and a repulsion with the calcium carbonates. That is our idea to explain. Now, why do I dwell so much on these technical issues, on which have nothing to do with large scale? Because this information we need, when we want to model how our body is degrading this material. And what we did so far is we have rather static data for specific degradation rates. We can also get static data from standard micro CT, but when we use synchrotron CT, we can really make a movie. We can observe the degradation process, and that's exactly what we did. We constructed a little sample cell here. This is about, this can be 5 millimeters, and the diameter is 1 millimeter or so, where we measured in situ how a piece of magnesium is degrading. And here in this little movie, you can hopefully see this. So let's see, I probably have to change my pointer. Good. So now it should work. Yes. So we can observe over many hours, here is the time, how this magnesium is degrading. We see here is a cut, here is developing something. We see slowly how the degradation layer is developing. We can nicely see it's by far not homogeneous, so we have to go back and homogenize our microstructure. And we can observe, do we have a constant degradation? Do we have accelerated phases, and so on and so forth, which is very, very helpful for our research. Why? Because we get, so I need to put my pointer again. With this unique data, we can now computationally approach the degradation. What we have a huge amount of information, not only about the time course and the individual development of the corrosion layer, yeah, what we can pinpoint, why is here a peak and why is here just a thick corrosion layer? what happened at this point chemically. We can see the distribution of, in this case, it was a silver alloy, little silver precipitates in the matrix. We can see that some of the silver is agglomerating here at the surface, which we have never ever thought of that this could happen. Nowadays, colleagues have done this for other alloys, and indeed, for some reasons, this silver, which should be distributed in the matrix, it's accumulating at the top of the material, of the corrosion layer, which if you think about an antimicrobial effect, of course, it's really nice. It's an add-on which we have never thought of. And all this is possible when we go for this degradation measurement in the synchrotron. Of course, we can then characterize volume changes, layer thicknesses, and all this. We can look for crack propagation even over a long period of time. And all this can then be used to model it. And Berit Zeller-Plumhoff, a very talented junior researcher, has come up with a model based on diffusion processes, which can nicely describe the degradation rates we see. And all this is based on the synchrotron tomography. Of course, a very interesting aspect, and that's what we also do in my institute, is how does this work in the living system? And we have the possibility to do in vivo tests. We have here, for example, 4 different materials. We made little screws out of it. They were implanted in a rat, or in several rats actually. We had 4, 8, and 12 weeks healing time. And during the life of the rat, we do in vivo imaging, and we try to again use that and the analysis we are putting on that data to also understand longitudinal how the material is degrading. But for the synchrotron, we are using an explant. So you see the screw, you see the bone, and we cut out a little piece here and analyze this in the synchrotron. And here you see an example of this. We have peak samples and a gadolinium screw. And you can see nicely that how much the screw here is already degraded. What is quite remarkable that you always see the shape of the screw. And that's very typical. Even when the material is completely degraded, it might still be possible that you see the shape of the screw, but it is not the screw anymore, which is actually a big problem for human monitoring, because on one hand, the screw normally has a very bad contrast in normal X-rays. And because the corrosion products which are formed have nearly the same contrast as the bone or some corrosion products, it is very, very difficult to say this is the screw or not. And I will come to that point a little later. So what we observe is, of course, that we have good connection or bad connection here with the peak. We see here is not a good connection. The bone is not growing on the screw. While for the magnesium, we see a very tight connection. We see the corrosion layer, but in principle, the bone is nicely on the screw. Now, of course, why are we doing this? This is nothing where you would need a synchrotron. We do this kind of experiments because we want to study load, and I come in a minute to this. First, I want to show you a problem we have, because the automatic segmentation of these data is by far not straightforward. So you see here an image, it's clear this is the bone somehow. It's also clear where is the screw. But what are we doing here in this part? Here is a close-up. Is this material or is this something else? Or is it bone or just an artifact? And when we put in histology section, we can see by the staining, everything which is stained in blue, it's a bone-like structure. So we have here a piece of degraded magnesium, which is not really visible in the X-ray, which is in histology clearly a piece of bone. And that's a big challenge for us now to come up with an automatic segmentation, which is able, when you get this data, to really identify which is which. And when you look into the screw here and you look at the different colors, you can easily see we have obviously different degradation layers. And it's not simple, just say, okay, this probably here somehow is the material and all this is degraded. No, it's not that easy. So we spent a significant amount of time to come up with computational tools for this automatic segmentation. And here you see when we make a cut through this, the standard grayscale thing doesn't work. Yeah, because we have a part here, which is screw. This might be a piece of the corrosion layer. This is corrosion layer. This is another piece of the corrosion layer. Maybe this still is another piece of the corrosion layer. And then here, this is bone. So it's very difficult to really analyze this. And we had one student who did this in a semi-automated way to identify and to segment these data. And this was then used in collaboration with a colleague at DESI, Philipp Heuser, who developed a neural network approach to automatically segment this by neural network training. And we got, I think, 2 or 3 specimens which were perfectly segmented by hand. And that took the student a year to get it really absolutely correct, assigned what is what. Then we did data augmentation, and that brought us to something like 100,000 images we could use for training. And with that, we could then analyze automatically our materials. Now, it sounds as if it works. I can tell you it doesn't. We have still some drawbacks. It's still not fully automated, but we are very much looking forward that this year we will have solved this problem. With this analysis, we could say, what about the degradation rates in vitro, so in the lab, and ex vivo, which means degraded in the animal and then analyzed after 4 weeks in the animal, 8 weeks in the animal, or 12 weeks in the animal. And we can see here in this graph, it's the same figures. Up to this point here in the middle, this is all in the lab, this is all in the animal. And the overlap here at 4 weeks, degradation in the lab and in the animal doesn't fit, which is no big news. The question was, is there any possibility that we can really predict what the degradation looks like in vivo from what we measure here? And what we can say is when we measure the degradation after 1 week in the lab, what we get is fairly good approximation what we have after 4 weeks in the animal. And when we measure 4 weeks in the lab, it's a good approximation what we get in average overall for a longer period of time in the animal. So we have some possibilities to predict what the material will do in vivo, but that's still a long way to go that we can say we know what the material does in the lab and we know exactly what it does when we put it in the animal. We can calculate, even with this not perfect automatic segmentation, for the peak and the other samples, the performance of our materials. And we see that after some time, it's absolutely comparable to what we see with from titanium. So a permanent standard implant material. And we were a little bit afraid that maybe the gadolinium, for example, would cause some necrotic effects in the bone, or that the degradation is too high, but we can see it works, and almost as good as titanium, in some cases even better. But of course, that's not the end of the story. I told you we want to understand the biological, but also to some extent the mechanical properties of this. And what we did here is that, again, at Petra, we designed, or we bought a little load frame, and we took this explant. So this is the 2 millimeter screw in a piece of red bone, and we are pushing on it. And while we are pushing, we are taking the tomograms, and you can see here on the left what it looks like and where the fractures are. And we are interested in how is this material and how is the bone fracturing? Where is the load impact highest? And you see here, for example, something happens here rather than here. And it's also that the bone is massively distorted, because we thought maybe the degradation layer is so brittle that you cannot use a load-bearing application. And again, for the analysis of this, you see that the whole thing is not stable, it's moving, yeah? And you see here the load curves. We had to come up with some algorithms which take account for this movement of our target, so to say. And Julian Moosmann and Stefan Bruns, two very talented scientists, came up with a digital volume correlation approach, which then, when it works, does not only correct for the movement of the whole thing, but you can also then automatically use it for crack detection, which will help us really to understand at which point of the sample do we have crack formation, how is that correlated with the corrosion layer or with the microstructure or with the surrounding bone. But all this is work in progress. It's much more complicated than we thought. And when we have that, of course, we have the parameters to go for an FE modeling of the biomechanics around this screw, which is our ultimate goal, that we want to know when we have certain bone to implant contact, for example, what is the load-bearing capacity of this implant. Last but not least, we are not only interested in tomography, but also a lot in the composition of bone, where we use diffraction. And here the idea is when magnesium degrades, magnesium as such, from a biological point of view, promotes the formation of bone tissue. But is it a biological formation, or can also the corrosion products themselves, which are calcium phases, calcium phosphate phases, something like hydroxyapatite, which is one of the main building components of a bone, can that be directly influence which bone structure we observe? And for this, we are working, and that's also not rocket science, with small angle X-ray scattering and X-ray diffraction. The problem here is to prepare the samples, because we need extremely thin sections, which in principle is not an issue, but to have the metal together with the soft tissue, and soft tissue in this case is the bone, that's really a challenge, I would say. So that was the biggest issue. And then again, we did the scanning experiments across the sample at Petra. And here you see an example. Here we picked one of the areas where we would have newly formed bone in the more, not in the dense region of the bone, in the cortical region, but here where it's a little bit loosely bound. And here you see where the scanning window was. This is what then the spectra look like after analysis, where we look, for example, for the despacing of the hydroxyapatite here. And we can look for titanium and the other three materials. Is there a difference? And we can clearly see that between a very hard titanium and a rather soft corrosion layer covered magnesium implant, that we have there some difference. And so far we deduce that the degradation layer is not directly influencing or taken up into the bone structure. But that was I think that was after 4 weeks healing. So we are now in the analysis for later healing stages, because the bone is remodeling. So there might be the point when this is directly taken up by the bone. So that was a kind of brute force through the magnesium implant development. I hope I could convince you that it was an extremely complex, or it is a very complex matter to develop such a degradable metal implant, and that in many cases we cannot compare our results with other materials, that we have influences not only here from the let's say chemical influences, but the way the cells and the tissue can also interact is something we have to understand much better, which is not the case at the moment. And that without really powerful in situ and in silicio techniques, we can probably measure forever, and we will never ever understand really the system. And a very good combination between this and very basic experiments will only give us the clue. So, but it's doable. So to come back to the title of my talk, I think it's all but fake news. We know what we are doing. It's a matter of time that we fully understand the whole thing. But then I'm absolutely convinced that these degradable metal implants will revolutionize the biomedical field for implants which have to be removed after the healing. So with this, I would like to thank my team from the Institute of Metallic Biomaterials, my colleagues from the Magnesium Innovation Center, all the colleagues from the Petra beamlines, which helped us, and many funding opportunities. And you see, some of the work was done together with partners from Malmö and Lund, where we still have a very strong connection. We even asked for some beam time with some colleagues from Lund, and unfortunately it was not granted to use neutron scattering to see the hydrogen evolution, but we are working on that. So with this, I'm at the end, and I thank you for your attention.
Thank you very much, Regine, for this extremely interesting talk. I would like to ask the audience here to please post your questions to Regine. You can do so either by posting them in the Q&A. You have a button at the bottom of your screen, or if you want to raise your hand, I should be able to see that as well. I think this really demonstrates how complex it is to work so close to real applications, how many techniques and technologies you need to use, and how complicated your samples are as well.
Absolutely. I mean, I always envy those people who are able to work on more academic samples, because then you can make them perfectly well for the corresponding technique you want to study with them with. But and of course we are also doing this for magnesium, but at the end we will end up with something which is produced by industry. And they have to take what they can buy. They will use their machines. That's why we have, for example, also part of the processing machines are the same as industry would use. Yeah, that we really do the same to the material as the industry. And then, of course, you end up with impurities, with all sorts of uncertainties, and then it's a big mess. So it's really difficult to find a balance between the very, very precise and very pure measurements, and the real stuff, where you more get a big average of everything.
Yeah. We have a question here from Alfred Larson. Would you like to pose it yourself, Alfred?
Sorry, I was still muted, but now I'm here. Yes, it was very interesting, and I was a little bit curious how you could tell that you had the silver accumulating on the surface from your tomographic slices.
Well,
do you get the chemistry from the contrast, or?
Well, it was an assumption, of course, from the contrast, and then we did a FIP cut and looked for it. Yeah, so we did not get it straight away from the tomography, but the tomography visualized that there is obviously something accumulating, which otherwise we would never have done the chemical analysis of the surface, because we thought that the silver is not accumulating. Yeah? So it was a very good hint, but it was not coming directly from that measurement.
I see. Okay. Thank you.
So actually, it's very typical, because we use very many methods. And when we see something in one method where we have an idea, or this could be this or that, we use another method to prove that. And for this, the synchrotron always gives us a very nice overview where to look at. Or vice versa, for example, when we have a good histology, or when we want to make a good histology section, we first do the synchrotron tomography, identify biologically interesting parts, and then we try to get an histology of that part, that we understand there must be something biological going on. So let's try to get the histology there, that we can see which cells are there, which cell products are there. So in that case, we're combining CT, not necessarily synchrotron, but also lab source CT is in many cases good enough, with histology.
So is it only tomography you use at the synchrotrons, or do you come back later for other kinds of methods?
Yes, so we use diffraction, of course. Tomography is nice because it gives us a three-dimensional idea. That's, of course, always nice. And you have pictures. Yeah, you can also nicely sell them. I mean, that's also clear. Right. But we also have experiments, a lot of diffraction, indeed, or small angle scattering. We are studying with colleagues who work on, that's not our work, but they work on corrosion protective coatings with grazing incidents, for example, how these protective coatings behave in a corrosive environment. We are looking in special geometries for twin formation under load, for example. So we try to use different techniques when possible, yes.
Yeah. So like I said, if you have a question or a comment for Regine, you can either raise your hand or write it into the Q&A box that you should have at the bottom of your screen. So do you, I mean, do you have any idea, like the time scale before this could start being trialed into humans or something like that?
Well, I mean, the materials we are investigating at the moment are actually not made to be trialed in humans. Yeah? We look for gadolinium alloys, for example, because we want to study, does gadolinium have a negative effect of whatever during the degradation course or even later on an animal, for example. Because this gadolinium is part of the currently used magnesium implant in the clinic. It's a rather complicated alloy, and we thought, let's just take the main component of this already in use alloy, yeah, make it more simple, and then study the effect of the gadolinium, because gadolinium is not present in our body. And of course, the people automatically say, no way, yeah, gadolinium is toxic. Yeah, but we have to think about the way we are releasing this stuff. We dope a piece of magnesium with some gadolinium atoms, yeah, because the concentration of gadolinium are normally rather low. And then we release this over time as an ion, which can either chemically form whatever. So we have found it, for example, also built in the hydroxyapatite. That would mean the gadolinium is staying in the bone. But it can also just bind to some transport proteins, and maybe then the gadolinium is found somewhere else. So in that case, we want to understand where is the gadolinium going. Yeah, and of course, if that works in the end, we can still say, hey, listen, we have here a nice material, it's absolutely safe. Who wants to produce an implant out of this? But it was not the intention. And the same for the silver containing alloy, where we want to see, is the hypothesis that the silver release from such a permanently degrading material, is that good enough to be antimicrobial? And for the cell culture, we have shown it works. And we are now planning for this year the first animal tests to see if we implant it, does it still work? When we load this material with really many bacteria, does it still work and kill them all? And then, of course, I think, well, that's my hope. Maybe I'm completely naive, but in the end, I hope when we can show it's antimicrobial and it doesn't harm the rest of the body, that the companies will say, yes, let's try that as well. But when you ask for a time scale, I would say 5-10 years minimum. For the implants on the market, the stent implant, I mean, stent, of course, is really very special because it's so dangerous. When a stent doesn't work, you are dead, right?
Yeah.
That took, I think, 25 years or so from the first idea, let's make it out of magnesium, until the approval was okay. Yeah, and for the screw, that was maybe 15 years, something like that, maybe 20, until it was really approved in the end.
Yeah. Do you think that process has sped up with practice, or rather become slower because of tougher regulations? Or you don't know, maybe? Actually,
it's both. So it has sped up because it is quite clear, as soon as at least one company has shown it works, yeah, then it is clear also for the notifying bodies and the approval authorities that they say, okay, it can't be that bad. Yeah, and when you are just slightly modifying something, but not changing the core of your product, to get the approval is relatively simple for a medical device. But on the other hand, as you say, the medical device directives have been changed. There is more and more testing to be done, and that will slow down everything, not only implant development. So that's really a problem. So in principle, the sooner when you have something on the market, this will accelerate that more stuff of this comes to the market.
Yeah.
But with the new regulations, yeah, that's a showstopper. That's pretty clear.
Yeah. So I think you've been very clear. We don't have any more questions coming in. So I would really like to thank you so very much for giving this really interesting talk, kicking off the colloquia again for us. I found this quite fascinating to listen to. And if this were normal times, we would have a bit of a mingle and eat some chips, but I guess we'll have to wait.
Well, I eat some chips here and think
okay,
of
we can do that. Yeah. So with that, I guess I would like to thank everybody for joining us, and thank you particularly, Regine, for this talk.
You're welcome. It was my pleasure. So take care and stay healthy, and hope to see you in live again soon.
That would be nice.
Okay, take care.
Take care.